In today's video, I want to show you how I went about solving exploit number 5, Sherwood-bank, found here on the Solidity Challenges repo. If you haven't already, go ahead, clone the repo, and open it up in your preferred editor. I'm now on the README for Sherwood-bank, where it states that it's a widely trusted contract, has recently come under scrutiny due to a potential security flaw. Your mission, identify the vulnerability, drain all the funds from the contract before anyone else. So our goal here, drain all the funds. Over on Sherwood-bank, it's actually two contracts. We have the Sherwood-bank contract and we have what's called Sherwood Money Handler. The constructor here takes in the money handler and sets it as an immutable. State variable wise, we only have one. It's a user balance. They do have a constant for minimum deposit. Function wise, we have three functions. And let's start down with the receive function. If you were to send value to this contract, it would simply create a single array, pass your address to it, and then call deposit funds. Deposit funds will take that address and take your value, check that it's greater than the minimum deposit, and if it is, it's going to run it through the loop, loop once in this case, and then it's going to call delegate call. The money handler is going to then apply your value to your user balance. All right, so let's dive a little deeper into deposit funds, because that was a flow for a single address, but it does take in an array of addresses. So the interesting thing here that jumps out is that, okay, we take an array of addresses, but we're only taking in one value. So that should jump out as a red flag immediately. If we have more than one address, wouldn't they have different values? And if they don't, if they only have the one value, does that mean that every address inside the array is going to be assigned the same value? Well, that's exactly what it means. So let's assume we have multiple addresses. And actually, let's assume for the sake of our attack that it's our address. And maybe it's not just our address once, it's our address multiple times. So if it's our address multiple times, and it's, again, say the Sherwood-bank has 2 Ether, and we come in here and we have our address in there twice, we pass in 1 Ether for each. Now our balance, as it loops through here, and it gets deposited by the handler each time, it's going to be our address and plus 1 Ether, our address plus 1 Ether. So I think we see the vulnerability almost immediately. Question is, how do we exploit it? Okay, well, there's one thing we need to know in order to do this is, first off, how much money or value is in the bank, and what are we starting with? So to get those details, we're going to move over to sherwood-bank.t.sol, and I'll quickly just look at the setup. I'll go through this in full later, but what we need to know is the deposited funds here. So the Sherwood-bank initially is given 10 Ether. So that's the value that we want to steal. And we are starting with 1.25 as we're defined as the challenger. Okay, so knowing this, we can start to craft an attack. So my attack contract, it may look a little big, maybe not. It's pretty straightforward. We're going to start by creating an instance of the bank, and I have this final recipient. And the reason I have this final recipient is because in the test contract, it actually wants the challenger to have the values. So in the end, if I didn't actually transfer value to a final recipient, the value would still live here on the attack contract and I wouldn't be passing that final assertion. So our constructor will just instantiate the contract and set the final recipient. We're left with an attack and a receive function. My receive function, when there is a withdrawal from the Sherwood-bank, it's simply going to transfer all the funds to the final recipient. Okay, our attack. In order to do an attack, we need to craft an array that we can pass to the deposit funds method. So we need to determine how many depositors we need. We know that the deposit address is going to be our address multiple times. So in order to do this, we need the balance of the bank, which we know is 10 Ether. And we need to know what our starting balance is, which is 1.25. So they divide nicely in this example. So that's 8. So we need to apply our address to the deposit array 8 times just in order to steal the balance that currently is found on the Sherwood-bank. So I craft an array, and then I fill it with my address, but I'm filling it 9 times. You'll see I state here. It's 8 times to steal the current funds, as I explained, and then 1 time because I want to get my initial deposit back. So 9 times. So once I have my array, I'll go ahead and I'll call deposit on the Sherwood-bank, and I'll pass in my balance of this contract, which at this time would be 1.25, and I'll pass in that depositor's array. Now that we're all set, we can call withdraw, and we'll set it up here so you can see both at the same time. And we'll jump back over here. So we're going to call withdrawal, but let's double back. I did call deposit funds. So we'll go through this one more time. Deposit funds. It has my array with my address 9 times. It's going to go through a loop. It's going to call delegate call. Delegate call allows the implementation of another contract to be executed, but also using the context of this contract. And it also has the context actually applied to the state of this contract, but allowed to use context like message value, message sender. So when we call the delegate call and we call deposit handler, the deposit handler, again, it has our message sender, so it applies it to our balance and it applies our value. It's not applying it here. This is a delegate call. This is required. You have to learn a little more about delegate calls, but the storage layout is critical. So this is required. But again, state changes happen on the parent, and that's why we have a user balance here. So our user balance is updated, and we now have 11.25 ETH, where we really should have only had 1.25. Nonetheless, now that we have our balance the way we want it, we can call withdraw. Withdraw is pretty straightforward. It just has a basic check that we pass, takes our balance as it sits, puts it in a variable, resets our user mapping, takes our balance, and then makes an external call to our contract. Our external call, like I say, it picks it up, and then we instantly transfer it to our final recipient. All right, so knowing all this, let's go ahead and take a look at the test. Drop out this contract. Now, the test from top to bottom, they have it set up where they create an instance of the Sherwood-bank, the money handler. They create a user array and an EOA for us. We're called Challenger. The initial setup will then deploy the handler. It'll pass the handler address to the bank, deploy the bank. They then create a user array of 10, passing 1 ETH for each address. And then they call deposit funds, passing in that user array. They didn't need to do this. It would have made no difference if they just had one user with a balance of 10 and passed it. I think it's just more to make us, perhaps get distracted. So it's a decoy. It's a decoy. Efficiency-wise, there's no need for that. Okay, moving forward. Challenger, so that's us. We're dealt our initial 1.25. There is a pre-check here to ensure that the balance of the bank is 10. And the challenger balance is 1.25. All right, here's where the action happens. They want us to execute here. So this was my attack. This was my attack here. So I defined the target, which is a Sherwood-bank. I defined the user recipient, which was the challenger. My attack, I deploy an attack contract. I pass in my initial 1.25. Again, we're pranked here as the challenger, so I have the 1.25. And I can even do that a little differently if I wanted to. I can do the challenger balance. So either way, and then we run our attack. And as expressed, we run our attack, and all the funds from in the end of that attack should be over on the challenger's EOA. So here, there's the challenger. The assertion is that the challenger's balance now is greater than 10 Ether, which really is the balance of the store. So there's different ways they could have put the test together. Nonetheless, the 10 Ether is the starting balance of the store. Okay, so it's time to see this in action. So we'll move over to the terminal where I have it preloaded. Give it a run. And perfect. So from the top, we'll go through this. You can see here we deploy our attack contract. We then call deposit funds. You can see we passed our 1.25 ETH, and our array is just our address 9 times. And then on the Sherwood Bank, the money handler is handling it. This is that loop now. It takes our address 9 times and applies the same value to it, 1, 2, 3, 4, all the way. Now we have 11.25 ETH. And the Sherwood Bank itself is going to perform the withdrawal because that was the next step in our attack. Okay, we have everything deposited, perform the withdrawal. It does that. It calls our attack contract. Our receive picks it up, and it passes the value of 11.25. Our receive function immediately calls the challenger, or the final recipient, but the challenger, and passes that value to him. So now he has the 11.25. The final assertion at the bottom here passes because the challenger's balance of 11.25 is indeed greater than that starting balance, which was 10. All right, so that was quick. I hope you got it all. Hope I didn't leave too much out. If you came across a different way of doing it, I'd love to hear it. If you want to talk about my approach, you can find my contact information in the details below. See you in the next one.